Hey everybody, Mr. Smith here. What I'm going to do is right now walk you step by step through the data gathering part of this Pivot Lab. It's really straightforward and it's got some cool tools on it that I just wish we had in real life in the lab. So first thing you're going to notice is that this defaults to height K, which is the tallest height. What I'm going to do in walking you through this trial is have all of us do the same one together. So the first thing we're going to do is hit change, and we're going to load up trial B by clicking the load button. So now we've got this little height right here. And what I'm going to do is open up the pivot tools, and the first one I'm going to grab is this horizontal red line tool right in the middle of the tools. And you can see the whole point of the horizontal red line is it can drag it up and down and it gives me some kind of baseline. So what I'm going to do is let this puck advance in the video until it gets down onto the flat section down here. And since it's all flat, it doesn't really matter where I grab it. But the technique that I want to do is with the horizontal red line, put that right in the middle of the puck vertically. That's important because the next thing I'm going to do is use that horizontal red line to get a vertical height. So let's go ahead, now that we've got that, just back that puck up back to its original position. And I like to use this new feature that they gave us, the red dot tool. So really neat. What I can do is just put a red dot right in the middle of the puck. So I've got it middle side to side and middle top to bottom, and that makes it really easy to see the next thing I'm going to do. So how do you get the vertical height? You click the vertical ruler, and notice that I can slide this ruler up, down, side to side. What I want to do is scooch the 0, you can see it right near this guy's knuckles, scooch the 0 so that it's right on my red baseline. Now that's smart because it makes my job really easy when it comes time to do math. So I'm going to put it there and slide it side to side enough so that it's easy to read where the red dot is. So you can see from my ruler, this is 1 centimeter right here, 2 centimeters, 3 centimeters, and so this first position of height is 3 centimeters. So that's a number that's important. It's the vertical height. I'll write that down on my data table and use that in a minute when we do the calculations. So before we get to the calculations, I'll show you the data you need for the end of the experiment, and we'll get that right now. What I'm going to do is open up the timer tool and just drag that off to the side, and we'll open up the horizontal ruler tool, and you can see you can drag that again side to side, up, down. And what I'm going to do is let the video play, and we'll let it play once through one time, and you can see puck speeds up as it goes down the hill, coasts when it gets to this flat part. What I actually am interested in is back up. I'm interested in the part where the puck is on the flat section. So maybe somewhere around there. So this right here looks like frame 123. That's fine. That's a good place to start. I wouldn't want to start the puck up here because it wouldn't be on the flat. It'd still be gaining speed. What we're going to have when the puck's on the flat is a section where the speed should be constant, right? So frame 122, let's go with that. I'll hit reset. I'll drag the 0 of the horizontal ruler just to the front of the puck, right there. Oops, I didn't mean to hit that arrow key. Right there. So now I've got the 0 centimeter mark lined up with 0 time. I'm just going to play the video until this gets to a nice easy number to read. Now I think 10 centimeters is super easy to read, and if I'm lucky, that worked out awesome. If I'm lucky, I was going to say that one of these clicks on the video gets the puck right to the 10 centimeter mark. So that turns out to be really easy to read. Okay, so here's what I'm going to do. 10 centimeters is the distance the puck's traveled. I write that down. The time that it took the puck to go that 10 centimeters is 0.1333 seconds. I write that down, and I've got all the data that I need. Okay, so the next step, what I'm going to do is show you what to do with that data. All right, let's go get it. Okay, so what we're going to do is test the basic concept now. Does all of the potential plus kinetic, all the mechanical energy at the beginning, turn perfectly into all of the mechanical energy at the end? So there's a couple numbers we can get. We have enough info to figure out mass times gravity times height because we made those measurements. We also have enough to measure the actual kinetic energy at the bottom from 1/2 mv squared. And because we made good choices and because we designed this lab to be pretty straightforward, this guy lets the puck go from rest, so I know that this number here is 0. And I also made sure, by the way I used my baseline tool and my height tool, that this PE was going to be 0. So what I've got, a pretty straightforward idea that I'm going to be checking out right now. I'll show you how it's done. Not tricky at all. So I know at the top I've got PE, and I know the formula for PE. That's mgh. And I'm going to go and convert my mass to kilograms. So 5.5 grams divided by 1,000 gives me that mass right there. Acceleration of gravity, 10 meters per second squared. And my original height, don't forget to convert it to meters. So 0.03 meters. So there we go. My original PE, 0.00165 joules of PE. Now, since we already know that KE at the top is 0, since this guy let go from rest, the whole point of the lab is to check and see, does this convert perfectly as follows. PE at the bottom is 0 because of the choices that I made regarding final height. And kinetic energy is going to be just, it's not a formula. You're going to get it from conservation of energy. The idea with conservation of energy is all the energy at the beginning turns into all the energy at the end with no losses. So 0.00165 joules has got to be the predicted kinetic energy. So that's the answer to the first question. That's your predicted KE. What we're going to do in the second part of the lab is actually test how well that comes out. So here's what that looks like. In the second part of the lab, we know that the puck coasted 10 centimeters and it took a certain amount of time to do it. Based on that, we can figure out its actual speed. So what do you do if you have a constant speed situation? The oldest formula we have in physics, distance over time. So 10 centimeters I convert to meters, that's just 0.1 meter. And it did that, the puck coasted that distance in 0.1333 seconds. And when I pull the trigger on that, I get 0.75 meters per second. So there you go, the actual speed of the puck. Why is that important? Because it lets us get the actual kinetic energy of the puck, and then we're going to close in on the finish of this thing. So actual KE, all I have to do is use my real 1/2 mv squared formula, put in the actual mass of your puck times the speed, 0.75 meters per second, and of course square it. And what we figure out is we get close, but not exactly the same as what we expected we were going to get. This is a little bit less kinetic energy. It's not 0.00165, it's 0.00155 joules, but that's our actual KE. So those are two more answers that you're going to want to get. Finally, how much were we off by? Here's the recipe you're going to use. Percent difference or percent error just follows this format always. So I take my actual 0.00155 minus the amount that I predicted and divide all of that by the amount that I predicted and multiply by 100. And in this case, what I'm going to get is minus 6.2 or 6.3%. There you go. Bring your questions to class, ask them out loud if you have any, and take care. See you soon. Bye-bye.